Okay, that's great. So thank you again so much for being so generous with your time and allowing me to present a couple different aspects of this story. And thank you all for listening to a little bit of my past also this morning. It's a privilege to get to share. So part two of the story of the connection between, or the relationship between network dynamics and the number of degrees of freedom in a neural network, which is characterized by the dimension. Dimension is another way to think about the complexity of neural network activity. In how many different directions is it varying? Do you have many neurons that are all working together to do one thing, a one-dimensional, 1 degree of freedom system? If you have n neurons, are they all doing something independent, maximal degrees of freedom, or is the situation, so an n-dimensional system, or is it something in between? Okay, and last time we talked about this from the bottom-up perspective. We did our best to review work of others in the literature, as well as to focus on some of the personal work that's been connected to our community in Seattle on this relationship between connectivity and dimension. So we said a neural network is described by its network, by its connections. And can we describe a general theory that relates properties of this connectivity to the number of degrees of freedom, this fundamental property of a neural network? Today in part two, we're going to take a top-down perspective, and we're not going to try to build a sort of general theory of all networks with arbitrary connectivity, with all of our limitations as well. We are going to focus on networks, specific networks that have learned to perform particular tasks or particular computations. And we're going to ask for those networks, which are the same type of thing. They're still networks characterized by a connectivity, but again, those are specific realizations of connectivity that are learned as opposed to general ones. What is the number of degrees of freedom that those networks produce in terms of their dynamics? Does that make sense? All right. So let's give it a shot. All right, so this is our new approach. At the core of everything is still, as it always was, a neural network, a dynamical system with a connection matrix W, right? That's all we ever studied. But again, this time we're training neural networks to solve tasks. And so what this means is the neural network is given an input. It processes that as a nonlinear dynamical system with network dynamics. And then that produces some output, which is matched to the input in some desired way. So let's just remind ourselves, this really is still a nonlinear network model. This is exactly the same as the systems that we were studying on Monday, or somebody would study in a bottom-up approach to network dynamics. The independent variables here are called H usually. That comes from machine learning, in which this is actually, someone tell me why they're called H. Can somebody unmute and share? I bet you know, please.
For hidden units?
That's great. And how do you say your name? Is it Ashina? Ashena?
Ashena.
Ashena. Thank you, Ashena. So Ashena is exactly right. So these are called hidden units. Why are they hidden? We're like, that's crazy. If the network, that's the whole object of my study. But from the machine learning perspective, they're hidden because they're not observed as the input, and they're not observed as the function or the output of the system. So they're in the middle, sometimes thought of as a black box code. So these are hidden units. I ranges from 1 to n, and this is time. So this is a discrete time system. You say the activity or the dynamical variable, the state of the system at time step t for neuron I, is given by what happened on the previous time step, the activity on the previous time step in cells J, summed up in connections from J to I, and then passed through a nonlinearity, or a general function f, which usually is a positive valued function. A rectified linear function is popular value, or maybe a sigmoidal function. Okay, and we'll just write that in matrix vector form. You have a vector of activity at time step t minus 1 multiplied by a matrix. Okay, so that is the dynamics, and you're training it to solve a task. So I have a task on the board, but who By the way, and I just wanted, for those of you who are new to artificial neural network theory, I'm pretty new to it. We didn't do any work in this area at all until a few years back. So even the basic definitions are new to me, and I might make some mistakes. So please interrupt me and say that's the wrong way to say that. But many of you will know that this is called RNN, a recurrent neural network. That's not feed forward, and it's called a vanilla RNN. This is almost always what people will mean when they say vanilla RNN. That means that these dynamics are pretty simple. You can have more sophisticated sort of substructures within the network. LSTM is a famous one of those. And then they would say it's a different network. But the basic idea, this is the vanilla or simplest form of a recurrent neural network. Okay, so now in terms of tasks, who can just unmute and share some interesting tasks that they've seen these type of recurrent neural networks solving either in the past or recently?
Speech recognition, handwritten recognition, or writer identification, text to speech.
Fantastic. That's very, very nice. And so these are recognition problems, mapping very complicated time-dependent or spatially dependent signals into categories of outputs. Is that right? So if you're recognizing a person, obviously I'm categorizing it as a Rava or an Ashana. And then how would you characterize actually the speech recognition? Is that's also mapping it onto an output, but it's a huge list of possible outputs, all possible words. Is that the right way to think of it, Ashana, or should we be thinking about it differently?
Yes.
Sort of okay, right? That's great. So those are all sort of complicated input-output problems. That's great. Okay, and so we're going to be studying a super simple input-output problem in order to try to understand the question at hand, which is about dimensionality and degrees of freedom. And we're interested in that for a variety of different reasons. Does the dimensionality in the brain match that of that in a learning network? If so, what are the similarities? If not, what are the differences? And also the basic questions that we brought up last time, which is that there may be more than one way from the perspective of the hidden layers to solve this problem. And are the network dynamics that are produced somehow optimal in a way that might be hidden if you're just looking at the solution of the problem? Are they good in particular for generalizing or extracting extra information about the signal? And we'll get into that in a bit. Okay, but the task that we're looking at here is simple. This could be like Ashana's different handwriting examples, but we'll do it as a face recognition problem. Your inputs lie in some dimension, and they belong to different categories. So all the globes here, all the circles might be images of Rava, like we had last time. The X's might be images of me, and the triangles might be images of Ashana. And they're different clusters, as we said last time, because Rava could have his Parisian image, or he could have an image in the mountains in Switzerland or whatever. So different clusters far away in input dimensional space, input space that have the same meaning. And by the way, that's why this is an interesting problem, is because I'm the same me, but when you see me big, or you see me small over here, those images are very far apart in pixel space or in input space, yet they mean the same thing, right? So that's what we mean by having far apart clusters of Ravas. Okay, so the input is given at time step 0 is a high dimensional vector. And then nothing happens for a while these recurrent dynamics unfold from one time step to the next. And then finally, after some period of time of thinking, the network is asked to make a report. And the report is done, this is important, through another set of weights, R, which are reading out the hidden layer activity into one of 3 different nodes, each corresponding to a different category. This is one specific way of doing this, but the idea is that if Rava was presented here, or an example of Rava, after multiple time steps, the output of this network should be such that this unit has a high activity and these 2 have a low activity. Sometimes you'll hear this referred to as one-hot encoding. Okay, some more terminology. So following on Ashana's helpful comment here, these are called hidden units, and we know why. And they produce dynamics, and it's that dynamics that we're studying. But in the machine learning field, the activity of these hidden units is referred to as a representation. And there's a humongous focus on these representations. You even have conferences that are very famous, like ICLR, International Conference on Learning Representations. There you go, it's in the title. And so notice in that title of the conference, or in the idea of the representation, it's not really about whether you successfully did this categorization, whether you called Rava a Rava instead of an Ashana when you saw him across the street. It's about what are you doing in the middle? And the most interesting questions, again, are you doing something in the middle that might enable you to do more than just recognize Rava? Are you producing some special representation of Rava that might be useful when you see an example of Rava that you've never seen before? So beyond the training case, or maybe even doing something even more, sort of extracting the essence of what it means to be Rava, what is the difference between a Rava and an Eric, and we'll get into that later. But the point is that there's a high focus on what is going on in these hidden layers, despite the fact that they're called hidden, and that is done in the context and the question of what is the representation that these create. And that's a big deal in terms of thinking about not how the network solves the task on what's called the training data, all the examples that it's seen before, but in how it might be able to adapt to new applications, either new examples or really qualitatively new ideas, like extracting the essence of what it means to be one person versus another. Okay, so H is often called representations, and then more terminology. This set of readout weights is doing one step of matrix multiplication, followed sometimes by a nonlinearity of these units. That's called a linear classifier, because again, the way that this activity H is mapped to the categories is via a step of matrix multiplication, one linear operation or just linear weighting going into each one of these nodes. Okay, so that's our setup. So what do we mean by training a neural network? And so with apologies to those of you who have seen this before, I want to go through this step by step in detail to sort of demystify, at least to me, this was all mysterious when I started, and really to illustrate to you how absolutely conceptually simple this whole process is. That doesn't mean it's easy, but there are really not very many tricks here, and there's not very much complicated mathematics either. So the idea is that let's call these units the output O, right? Input, output. You have something that you want to have happen, which is the target, which is what the output should be at time capital T, right? Again, when a Rava is presented, the target should be the vector, say 1, 0, 0. Okay, so that's OT. And then you have what the network actually does, right? Which is on time step T, it's going to take the activity, H at time step T, it's going to apply a nonlinearity, and then it's going to apply these weights. And that gives you the output that may not be your ideal output, but it's what the network is outputting with the current set of its parameters, W and R. You define a loss, which is how accurate you are, which is the Euclidean distance. In this case, you can use other distance metrics between the actual output of the network, which is O hat, and the target output. And then, unless you are perfect, which would mean that the loss was 0, you improve the network. And this is the training step. And the idea is you take whatever weights you had before and you change them by an amount delta W, a matrix valued amount delta W, in order to improve the loss. And what that means is what it sounds like it means. You literally compute the gradient, or the direction of steepest descent of the loss, with respect to all possible matrix value changes in W, and you update by an amount eta, which is called the training weight, going downhill in that steepest direction to try to minimize the loss. That's it. And you do the same thing for updating these readout weights. Okay. So let's do this. Let's actually compute or go through a couple steps of computing what the gradient with respect to weight is of this loss function. Okay, so the first thing that you see, what am I doing? These O's depend through some, through some relationship on W. So I'm going to be taking the derivative of this term with respect to W. I need to use chain rule, right? I won't go through all these steps, but the first thing that's going to happen, sorry, there should be a minus sign here, but the first thing that's going to happen is this 2 is going to come down in front, and you have something that looks like OT minus O T hat, that's this term. And then by chain rule, you still have to take the derivative of the thing inside the expression that depends on W, which is the second term. Okay, I think you see what I'm doing. So now what is the derivative of the second term? Let's remind ourselves that OT hat is R times F of HT. So where does W come in? Well, let's just write that down. So R times R times F of HT. Where's the W? Well, the W comes in when we remind ourselves that HT, right, is a function of the activity of the previous time step that involves W. Okay, and so we finally see W showing up when we've unpacked the dynamics by one step in time. And you see that all I need to do now is take the derivative of this nonlinear function, actually twice, with respect to the parameters in front of W. Oops, but then I have to multiply that by the activity that was actually there in the system at the previous time step. What is that? Well, I can write that as a function of the activity at time step t minus 2, t minus 3, and so on and so forth until I get all the way back to the activity that is determined by the input on step 1 or on step 0 in time. So in this way, the gradient depends on W many times over, and that dependence of W is modulated or multiplied by the activity of the network at various points in time in computing this gradient. This is why this is called often a backpropagation through time, because the activity of the network at many points in the past influences the sensitivity of the network activity of the time you care about, T, to the weight matrix W. And it's that sensitivity that you're trying to understand so you can best reduce the loss. Okay, so why did I go through all this with you? Two things, to show you that this is, why this is called backpropagation through time, and to emphasize two things, that the network activity at all points in the past influenced these updates. That's an interesting general fact to think about for biology and for learning. And also to emphasize that these calculations are completely straightforward, right? This is just calculus, and this really is the way you work. You do this calculus and you type it in to a script, which is doing these updates, or you use a modern method like PyTorch or TensorFlow, which are packages that many of you, I'm sure, have used that do what's called automatic differentiation, which is computing these gradients for you automatically. Okay, so that's all we are doing underneath the hood, and let's see what happens. Okay, so we're going to train this neural network to solve the task that we're talking about. And again, what we're concentrating on is not whether the network solves the task or not. Something like this sort of categorization of different clusters is not a challenging machine learning problem. We're going to be interested in what is the representation that is formed, and in particular, does that representation have special and interesting properties from this viewpoint of dimensionality? And to underscore that point, actually, let me stop here. I'm sorry, I'm not doing very good lecturing technique. Who has questions or points of anything that's not clear on anything I've said before? Or just points or remarks or additions that you wish to make. Many of you will know more about many aspects of modern machine learning and AI than I will. To this. Okay. So let's look at this example. And again, I'm going to make this problem even easier than I said it was, or the easiest version of this problem, let me say, in order to, again, emphasize our, or sharpen our focus on this question, right? It's not can the network solve the task, but how does it solve the task? And what are the signatures of our artificial brain's activity as it is solving the task? Okay, so this task is made easier by casting the inputs in very high dimension. And as we mentioned last time, as you can see from this image, these inputs are linearly separable from one another. So in a sense, this network could solve the task without even any help from W. All it has to do is copy the input into its activity and then learn the correct weights. Remember, these weights are just like a linear classifier. And then that process could solve this problem of categorization with 100% accuracy, again, because these inputs are linearly separable. Okay, so what is the dimensionality of the activity that the network learns? Okay, and how does that compare with what a network, which is observing that this is linearly classifiable, not changing the input around much, just copying the representation in and solving this problem via the readout weights as a linear classifier? How different is the dimensionality of this learned network from what you would get if you just, again, took a simple representation or copy the representation in and solve the problem with 100% accuracy with just the readout weights doing all the work? What happens when this network learns? Okay, so first of all, we have to characterize the dimensionality of the input, and that depends on how many clusters of Ravas and Erics, in this case, you take. If you have a picture like this with a total of roughly 4 clusters, then the dimensionality is something close to 4, right? If you, it's really closer to 3, but if you take 3 blobs of points, like we said last time, that makes up a plane, so that'll be 2-dimensional. If you add a third one, that extends into a 3rd dimension, etc. So as you look at different versions of this problem with more and more clusters of Rava or clusters of Eric, the overall dimensionality of the inputs goes high. Okay, and that is the baseline against which we will compare the representation in the neural network. What is the representation dimensionality? What is the dimension that the network learns when it's solving this task? The answer is the green line. Okay, and the first thing to notice about the green line is that it's very low, right? So somehow the network is absolutely not doing a copy of the representation, even if it's initialized to just copy the representation by W being the identity matrix, say. It is absolutely not just copying the inputs in and then learning to linearly classify them. No, it is massively reshaping the inputs. It is creating a representation of the inputs, which is gigantically shaped and reformed and completely different than the way the inputs are laid out in sensory space or in input space. And it's only after it massively changes and reshapes the representation of the world that it makes its decision, that it performs this classification. Okay, that is what happens. Let's look at that in movie form. And again, that's just a result of doing calculus and iterating the calculus steps that I showed on the previous slide. It's absolutely nothing else. Okay, but let's see what this phenomena is. So again, we'll look at this now in movie form. So this is some sort of high dimensional input, a lot of blobs of Rava, a lot of blobs of Eric. And this is living in who knows what, 30 or 40 dimensional space. And of course, it just looks like it's living in the plane because I projected it onto the computer screen. So that's what the input looks like, which is also the activity in the neural network at time step 1. I should have been more clear about that. Okay, but that's the input to the network. That is the input representation. And we're going to watch a movie now. And the movie will be from one time step to the next, the way that a trained neural network, so a neural network after training, reshapes these inputs to form its representation over time. Okay, here's the movie. Let's watch it again. So here's the input data at time step, which is also the representation at time step 1. But then the learned W, right, the learned network dynamics, massively reshapes, as promised, these inputs into the neural network's representation, which evolves over time. And you can see that all the Erics are squashed together to a point, and all the Ravas are squashed together to a point. And what this squashing is doing, of course, is taking blobs that are originally distributed all over the place in 40 dimensions, a 40-dimensional set, and squashing it down into one blob over here and one blob over here, right? So the total dimensionality of the data after you're done is one, right? One line connecting these points. And so that's what we see with a squashing of dimensionality. And I want to emphasize that this is something that does not happen in a neural network that's initialized with, say, identity weights or random weights that are close to the identity. If you just initialize the network, it basically leaves, can leave, and in these examples, it just leaves the dimensionality alone. It's not reshaping the representation by virtue of its initial weights. This representation reshaping and this dimensionality squashing is something that emerges across stages of learning, which are called training epoch. That's basically how many delta W updates have you applied. And it's also, as you saw here, something that occurs over time, right? This is more studying the network dynamics. And again, that's something that you saw at time step one. The dimensionality is full because it's just the inputs, but it's the W acting on these representations that cause their dimensionality to get squashed. Okay, who has a question about what the movie is showing or what this plot in the lower left-hand corner is showing? Yes, Shui.
Hi, first, so my question is kind of, I really like the example you used to how to classify face into two categories, right? I wonder if we store the memory of the process. See, now I know who's Rava and who's Eric, and if I just look at like one angle of you, do I still know that's you? I mean, this network is, yeah, I don't know how to explain that in a mathematical way.
Yeah, you know, I think that's a great point. So that is why these problems are challenging, right? And that is why all the Erics are not clustered together here close, right? They're spread all over the place because in input space, like you're saying, if you would just take, you know, the pixels on your Zoom screen, right, and make them into a big vector, right? A megapixel image would have a 1,000,000 element vector, and you would look at that vector when I'm standing here, and you would look at that vector when, oops, I almost fell off my treadmill here. That's interesting, over here, or when I'm really small, or when I'm backwards, or when I'm in the dark, or when you see the side of my face. Those are very large changes, right? So these inputs are all over the place. And then the problem of actually solving this task is being able to say, well, these initial inputs are all over the place, but I'm going to put them all in the same category, right? And as I was trying to say, even though that sounds like a sort of hard problem, it's not if the inputs are high dimensional, or at least doing this separation is not a hard problem because high dimensional inputs are always linearly separable. But the challenge is the one that you described, and that clarifies why we're focusing, I think, on representation and dimensionality, is that if you have these very, very high dimensional inputs, there are lots of parameters that you have to learn in order to figure out where the separation boundary is, right? And maybe with lots and lots and lots of examples, you can do that. But who's to say that a new example of Rava in a city where you haven't seen him before will be well matched to the examples on what you've learned. So maybe you'll be very good at your homework, at all the problems that you've learned on, but when you come to the exam, which is a new question, you'll get it wrong. And that's the type of thing that can happen when you are doing learning in these very high, as I understand it, is when you do these learning, this learning in very high dimensions. The idea of doing forming a low dimensional representation might be that new examples of this Rava, or new examples of this Eric that you haven't seen before, will also get moved to the same point in a low dimensional representation space in this case, and so in a low dimensional representation, so that whatever you learned in terms of the parameters of your classification rule before will continue to apply after. Does that make sense?
Yeah, so you mean if we have new representation, that would be automatically kind of classified into through the network would be classified. But I wonder if we have memory from the previous input.
Yeah, I understand what you mean. So it's really a dynamical process. And then the inputs would be like movies as opposed to static images. And that's a great question. That is not something that we've studied in the context of this recognition problem or this classification problem. But that is a really interesting idea. I'll share some results in the end about prediction as opposed to classification, which will maybe move in the direction of more dynamical inputs. But yeah, to the extent to which these dimensionality questions are open, thinking about the evolution of dimensionality for networks that are processing time-dependent signals is a great idea, and I think it is really interesting. So thank you.
Eric,
Go ahead.
Eric,
Yeah.
are you're standing on a treadmill?
Either that or I'm falling off of a treadmill, but it's not.
So you're walking as you're giving your talk?
Not now, no, because it broke. And when I'm trying to concentrate, like now, I'm not walking. But yeah, that's my work from home setup. Yeah. Okay. Anyway, it's sort of brilliant until I break my leg. Okay. Anyway, so I think it sounds like people are very clear on what's happening in this network. I don't think I gave a very good description of why this is useful for generalization. Maybe you should learn from that, that I don't really understand that very well. And I'm saying this vaguely. There are some formal relationships and some things that are known, but really understanding what these low dimensional representations are good for in practical cases is maybe a reasonably open problem that somebody other than me, somebody like you, might be able to solve. It also may be a question that our group should concentrate on more in the end. But I think what you can see from these movies is it's unquestionable that these neural networks massively reshape their inputs, and they form representations which are spectacularly different from the representations in the input on the way to solving these tasks. And I want to emphasize for the last time, I know I've said this a bunch, that is not a necessary reshaping in order to make these inputs linearly classifiable in this case. I've chosen this case because it isolates this reshaping of representations for some reason. It isolates that this reshaping of representations happens even when it's totally unnecessary from the perspective of making a representation that the readout weights can operate on, because these data are completely linearly separable. The linear classification accuracy is 100% accuracy all the time. Before you train the network, it creates totally separable representations. After you train the network, the representations are totally linearly classifiable or linearly separable. At time step 0, which means just looking at the input data, the inputs are completely separable at any time step into the future, including after time step t, where the loss is evaluated, the inputs are totally linearly classifiable. So again, this is why this lecture is occurring in a series on network dynamics. This is somehow an artifact of the learning process taking place in a network, as opposed to some sort of requirement for this loss to be minimized for the task to be learned. Okay, so this is my yellow summary. So trained neural networks seem to produce a very strong and compression of dimension, and I call this unnecessary because it is an unnecessary compression of dimension from the perspective of learning how to classify the data with which the network is presented. It is not at all apparent in the loss function or in the structure of the network, and therefore it's interesting. I want to emphasize that here we had sort of an extreme form of this compression where the neural network squashed all the Al-Rabas and all the Erics into a point. That doesn't always happen. Sometimes you have dynamics that look like this, where you have very high dimensional inputs, and then the learned network processes those inputs by squashing together all the Erics and squashing together all the Rabas, but not down to a point. This squashing occurs down to lower dimensional sets which look sort of like transient versions of chaotic attractors. And so I'll call them that. You can characterize things called Lyapunov exponents, which many of you will have studied, which are how many directions of instability there are in the system, sort of like generalizations of the idea of eigenvalues with positive real part for linear stability analysis. So those positive eigenvalues, as positive Lyapunov exponents, are a signature of chaos. And it's probably true that in some cases, these neural networks are learning to produce low dimensional representations, which are complicated low dimensional attracting sets as opposed to just points. Okay, so we'll say chaotic attractors too. And the papers that contain these results, I think one of them I provided as a reference is by Matt Farrell several years ago. And Marav Stern has also developed these results, and we'll talk about her work in a little bit. And she has an abstracted cosine on this. Okay. All right. So we've seen that there is this gigantic network-driven collapse of dimensionality that occurs in neural networks, recurrent neural networks that are learning to do tasks. And the first question that might come up is why, right? What is the mechanism for this collapse? Okay, and in order to answer this, why are networks learning to do this collapse? We're going to build a toy model that we can more or less completely analyze. Okay, so how are we going to turn this system into a simpler network? We'll undertake a series of dramatic simplifications. Okay, so here we go, building a toy model. So the first thing that we're going to do in making our toy model is replace the complicated blobs of Ravas and Erics with just a big grid of Ravas and a big grid of Erics. Okay, this is really just for visualization. The next thing that we're going to do is concentrate on how the representation of just one of these categories, just the Ravas, changes as the network learns its representation. Okay. And then the third dramatic, the inputs into the model are going to be just this grid, one big set of Ravas. And then the last major simplification that we're going to make is we're going to replace these truly nonlinear dynamics, right, which apply W multiple times over T time steps with a nonlinearity every time, with a simpler model in which we've linearized this F. We've gotten rid of the F, change it to the identity function. And in that case, we're just applying this W operation once. So it's a one time step linear recurrent neural network, which ends up being equivalent to just a linear feed forward network, or if you wish, even simpler, just matrix multiplication by a matrix W acting on the inputs. That is the entire dynamics of my simplified network. Okay, who has a question about that? Violent simplification to build my toy. Okay, and so that is it. That is my total dynamics, right? I take my inputs, I multiply by my weights once, and then I get my hidden unit representation. And it's based on that hidden unit representation that I apply my linear classifier to solve the problem. Okay, so geometrically visualizing what's happening is nothing more than saying the network takes its inputs, which is this square or grid of inputs. It applies its weights, which is just matrix multiplication by W, to those inputs. And then it produces a representation. And that representation, after one step of matrix multiplication, is going to be a rotated, possibly flipped, and stretched in different directions version of the original input grid. Okay, so the question is, well, what's going on? When a network learns to solve a task with these type of simple dynamics, how is this representation different from the initial representation? And is it a gigantically compressed representation in which the dimension is way lower than that with which we started? Okay, to define that, we need to make sure we understand the way learning works. I want to emphasize that once again, there's a linear classification R that's applied to these hidden states. And the goal here is for this R to read out this hidden unit activity and give the answer +1, because these are all examples of Rava, not Eric's. So in this case, since we're thinking about just one category, the readouts will just be the vector that is pointing into this one output. And our only desire in this simple form of the problem will be that this output takes the value 1. So that is a very simplified version of the problem. Let's copy it again. Here are your inputs that are acted on by W. And that forms a representation here of those inputs, which I'm drawing very huge. Again, remember that in general, this representation lies in very high dimensional space, even though I can just plot 2 on my computer screen. And here's what this representation would look like if W wasn't doing anything at all. If it was just a copy of the identity matrix, and the representation would just be the same as the inputs. Okay, any questions about this? Okay, so in particular, how does this work when we take just one copy of Rava here? So just the giant blue Rava, well, that's going to be mapped to somewhere in representation space. Okay, and we remember what the target is, which is that you take the dot product or just read out this hidden unit activity by multiplying it with a vector R, right? That's projecting it onto this vector R, and that is supposed to be equal to +1, okay? And what that means, of course, is that this dot in the representation space needs to lie along the line, which gets projected onto the value or the length of this vector of 1. In other words, this target will be perfectly satisfied with 100% accuracy if this blue point lies along the blue line. And if the blue point is not along the blue line, or actually the blue hyperplane, then you will have a non-zero value of the loss, right? The dot product of your input sample, your represented input sample with a readout weight will not be 1, so this loss will be non-zero. So in this case, is the loss 0 or non-zero? It's non-zero because you're not on the blue line. And so we need to do some training, and that training occurs via exactly what I talked about on the early slides, what's called back propagation, which is the same as gradient descent. So I update my W matrix away from its initial value by some increment, delta W. And the hope is that this increment helps in terms of reducing the loss. Okay, so let's just look geometrically at what this delta W does to the representation in this example. Okay, you ready? This is before the delta W, and this is after the delta W. Now I'm acting not just by the identity, but by the identity times some input. And the representation of the blue point changed from what it was before to what it is now after. And the representation of these other points, of course, changes as well. Okay, so based on this, could somebody just unmute me and unmute and say whether it looks like learning helped? Before learning, after learning. Did it help? Somebody just unmute and say yes or no.
No, but it makes the error smaller.
Okay, good. So I would say it makes the error smaller. And I guess maybe I wasn't very clear on saying what help was. For me, helping is reducing the loss. So I would say that it did help. So it's made the error smaller. But sorry, I wasn't very clear in what I meant by that, I know. It made the error smaller, and I would say that that indicates that learning is working. At least this example of Rava is moving closer to the blue target line. Okay, but there's a really interesting observation that some of you may have been able to see mathematically, or, well, I wasn't able to see it, but maybe you were, or at the very least we can see this geometrically, which is in what direction did this blue point move? It's kind of an optical illusion, but does anybody have any remark that they can make just by watching my movie? Which direction is the blue point moving under the learning?
According to the blue line.
It's going straight into the blue line. It's moving directly into the blue line in the direction of the readout weight R. And that's actually something you can establish if you just take the simple toy model and do 1 or 2 steps of calculation. You can see that these delta W updates are always rank 1 updates, which are some more complicated vector that has to do with the details of the problem. and the sample, but it's always multiplied on the left by a column vector, which is R. Okay, what that means is that any changes in the weights, when they're then applied to any inputs, right, through matrix multiplication, any of these updates will do something, but that something will be expressed by through a change in the R direction. That is the range of these matrix updates using the linear algebra terminology. So the only updates that will ever occur via backpropagation always move points in the direction of the readout. That's one direction and in no other direction. That's an interesting fact. So let's look at the consequences of this by repeating many of these steps of learning over time. And that's the movie that you're seeing now. You can clearly see that the grid of representations of RAVAs is not moving all over the place. Every individual point is changing, it's compressing, it's going toward the blue line. So learning is occurring, the loss is being reduced. But the way that the representation is being reshaped is only by shifting points in this one direction along R at every time step, at every step of learning. Okay, so here's my question to you to unmute and share. Is this type of learning reducing the dimensionality of the representation? And if so, by how much? Let's just think about that for a second.
Well, it looks like it does, and just by -1, probably.
Whoa, fantastic. Okay, Lydia nails it. That's exactly right. So thank you. Sorry, Lydia, am I saying your name right? Okay,
Yes,
Lydia
yes.
has it exactly right. So yes, they're compressed along this R direction. We can see this very clearly. It's like a skewer and all the points are sliding along the skewer. Americans may, well, we borrow it from another country, I'm sure. Shish kebab is a famous expression, right? Where you have all your vegetables and you have a skewer, whoop, and you slide them along. Well, it's like I have a shish kebab, which is this R, and I'm sliding everything along it, right? So the states are compressed along this R. And just as Lydia said, this does reduce dimensions, but it only reduces dimensionality in this one direction. The other, in general, n-1 dimensions are completely unchanged. I'm just collapsing along one dimension. So if you have high dimensional input data, this is not going to make much of a difference to the dimensionality. This doesn't really make a low dimensional representation. Just shaves one dimension out of, say, 300 off. So it looks like this is not working, right? In terms of characterizing, this is an extreme toy model, but this is a toy model that fails to reproduce the phenomenon that we see in the full network simulations. Okay, who can make some suggestions as to what was missing when I oversimplified things to make this toy model? What is one of the, I removed a lot of stuff, right, in making the simulation and in making the model and really the way that I use the model. And if you remember back to all the slides, which I definitely wouldn't, but if by some flash of insight, and you know more than me, which is probably true, you can think back to some of the earlier slides. What are some of the things that happen in the real network training that are not happening here? So what are some of the ways that in building this toy model and running it like that, I might have oversimplified compared to the full system, which is this one, right? Nonlinear network, multiple steps. What are some other things that we might look back on? Okay, let's look at this loss. Oh, hang on. I see that at every step I'm updating the weights, but I'm also updating the readout weights, delta R. I update all the parameters in this network. And in my simple simulation here, right, I built my toy model, right? But in running the toy model, I took the readout direction to be fixed at every time step, right? And when the readout direction was fixed at every time step, there was only one direction by this mathematics, which is cute mathematics. I like it because it reminds us that then when this readout is fixed, then there's only going to be one direction of collapse. And Lydia's comment is right. That's not going to be very effective in terms of reducing the dimensionality. It's just going to do it in one dimension. But that's not the way that training works in neural networks. You have separate updates going on at every place where you have weights. So these readout weights will not be constant. They change around on every time step according to that update rule. So what does that mean? That means that sometimes the readout weights are pointing in one direction, forcing you to compress along this R or to this blue hyperplane. Sometimes they're pointing in another direction, forcing you to collapse to this blue hyperplane. Sometimes they're pointing in the middle, and in the end, you get compressed in all these different directions, and you're trying to live on the intersection of all of these different planes, which define not just one readout target, but a whole set of different targets. And as we all know, the intersection of a bunch of planes or a bunch of lines, or let's say a bunch of planes, is going to be in general much lower dimension than the intersection of than the planes themselves. If I have enough planes, they will intersect only at a point. So that suggests that this picture changes when the readout weight changes. And indeed, if I make a simulation in which the readout weight is changing, so these blue target hyperplanes are changing at every time step, I see that now I'm forced to compress not just in one fixed direction like I was before, but now I'm compressing in a wide variety of different directions. And as a consequence, my overall grid of points is not compressed in just one direction, it's compressed in many directions. And as we see, I do not end up with just a line. I end up with this set of points, which is gradually getting squashed again in all directions. So if you have readout weights which are being co-trained or otherwise, at least from the perspective of this linearized model, if the readout of the network after the representation is formed, or at least after one step of the W is formed, acts on the representation. If everything downstream of that changes from one time step to the next, like you would expect, again, with co-training of the readout weights, you would also expect that from other mechanisms that we can discuss. But if that is changing from one time step to the next, you'll get compression in many different directions. And therefore, many dimensions will be reduced. So I think that a fundamental mechanism that leads to these low dimensional representations, which are occurring automatically when we're training recurrent neural networks, is a very simple one. It is simply that there is not one objective that the network is trying to learn according to one set of readout weights. But you have fluctuations in terms of how the network output is being interpreted, and therefore you have fluctuations in the constraints that via this mechanism cause collapse of the input data along many different dimensions.
Sorry, Professor. Can I have a question?
Oh, absolutely. That's the whole point.
So if you train the W while you also train the R, the read output, so how can you make sure that the system will finally converge to the stable state?
This is such a good question. Okay, so I love your that's very, very good thinking. So here what I've done as, what is your name?
You show.
You show, as you show correctly determined, I kind of cheated, right? Here I cheated, I'm always cheating, right? Here in my first toy model, I was really extreme by holding R fixed and articulating that that is not what we need, that is a failure. In the other case, I was sort of cheated in the other direction by just grabbing R and changing it around by hand, right? And what you show is asking actually is this, which is, so this is something that you can prove if you take R and just move it around by hand, that this will lead to compression. But what you show is asking is, what if you take the actual changes in delta R that occur from co-training in a mechanism like stochastic gradient descent? And it turns out that you can prove So in at least I think the same version of the paper that is here and one that I shared with the class, you can take the actual delta R's that result from this process of stochastic gradient descent. What that means is that you're just taking a different sample on every time step, or a different set of samples on every time step, or I'm sorry, on every parameter update step. You're taking a different set of samples. That causes some variability, it turns out, in the readout directions, and you can prove under certain conditions that that is enough variability in order to cause this collapse to a point in these linearized networks. So you asked a fantastic question. If you were here at the University of Washington, maybe you're a postdoc, that would have been a nice paper that you would have motivated and written. So very, very good question. I think this is, let's see here. Let's see, I think I'm not going to take the time to go through. Well, actually we can choose. Maybe what we should do is, let me ask a question. Would you like to hear maybe 2 minutes or so worth of details in the answer to Yusho's question? Yes, okay. All right, so since she asked it, it's a very nice question. Here's the way this works. Okay, so you have the readout that's pointing in a particular direction at a particular stage of training. And you take a new sample here for the next stage of training. It turns out that the direction in which R gets updated is in the direction of the sample that you're taking to evaluate the loss and therefore update the parameters. So what will happen is a readout direction that pointed originally in the direction in one direction is going to be updated to be moved more in the direction of your next sample. Okay, and as we just saw, the changes in the direction of R, then on the next time step, sorry, that's another piece, I'm sorry, the changes in R on the next time step will be proportional to the changes in W, and then the changes in W will be proportional to the changes or to the changes in R, as we just saw on the previous slide, where the updates to W were always rank 1 updates in the direction of R. So it's so in other words, in stochastic gradient descent, you always have changes in R that are pointing in the direction of the new samples that you're taking on that step of gradient update. Those then feed back to impact what the weights are. And then on the next step, you have another sample, which will change the readout direction. And it's the iteration between these two processes that you have to study if you would like to know under what conditions these samples are basically spread out enough so that they produce enough variability in order to drive enough variability in R in order to drive a collapse of the dimensionality of the system. Is that okay? Is that a reasonable answer?
Yeah, maybe I can check the paper later. Thank you.
Okay. Oh, I'd love to talk about it more. Thank you. I think one other remark that's worth making here. So this is about mechanism. So, and then maybe, Rava, would it be okay if we take a little break in just a minute or so?
Yeah, actually, I was going to suggest that whenever you want, we could take a break, sure.
Yeah, that would be fantastic. But I just want to review where we are, and then we'll take a break. So what we have seen is the following phenomena, right? When you train a neural network, this seems to be an ubiquitous phenomenon. You start with high dimensional activity, and for no reason, at least for no reason from the point of view of preparing the data to be read out or classified, you do not leave these data alone. You massively squash them together, right? Gigantically reducing the dimensionality, right? A picture like this. And we want to know why this happens, because again, it's not at all apparent from the loss function itself. And so what did we do, right? So we suggested one mechanism, and that's the mechanism that we've just been discussing, right? In terms of this movie, right? The idea that you have readout weights that are changing, and if you just actually mathematically compute what back propagation is doing, it's always squashing you in the direction of these readout weights. And if there are many different readout weights, you'll be squashed in many different directions, right? So this to us says that there's always a mechanism present in neural networks, which is going to produce these low dimensional representations. That does not mean that this is the only mechanism that can produce low dimensional representations in neural networks. For example, if we go back to just the definition of our network activity, network dynamics here, for example, who can tell me a form of f, a nonlinear function f, which would lead to strong compression of representations, say from one time step t to the next, t minus 1 to the next time step t? Can anybody think of a form of f which might, even without any variability or any learning, tend to produce a great compression in the representations? Question. Let's see. What if? This is a typical Zoom background problem. But what if that function f is, I'm a human blackboard, is like a sigmoidal function, right? Which is squashing inputs on top and squashing inputs on the bottom, right? With a maximum of plus or minus 1, right? Then the only possible outputs of this function f for very extreme values of the inputs would be plus or minus 1. And that's a compression to one of two possible states, right? Almost like the original Hopfield network dynamics, which were binary on a cube, right, for example. So that says that you could have a nonlinear function f, which itself builds lots of compression into the network. That's another possible mechanism. So all that we're trying to say, or I think that the take home from this is, from this toy model analysis, is that in the simplest case ever, get rid of squashing nonlinearities. Don't worry about saturating these nonlinearities. Don't worry about having a special form of f. Don't worry about anything. Build the simplest model ever, in which you have co-training of outputs and recurrent weights. Or even if you have sort of effective changes in the output weights, because, for example, the location in state space where you're doing this linearization is changing over time, or there are multiple downstream layers that are also being co-trained, or there are multiple iterations of the same network W on future time steps, which will affect basically the way that these signals are read out. Anything that introduces that type of variability in the training process, or in a brain, if there's noise, any of that will cause compression as well. So it's like a scenario in which all the players are on the same team. Nonlinearity and might give rise to compression. This variability might give rise to compression. Noise might give rise to compression. And so these networks seem equipped to do massive compression to form low dimensional responses by many factors working together. And that is maybe a good point for a break. And what we should do next, I think, is to ask whether there's any evidence for anything like this in biology and what this might mean in terms of computation. But for now, it's just an observation about representations. Is that okay?
Yeah, that's great. Thank you very much. That's great.
Let's drink coffee. Yes. How long do we have?
Should we start in 10 minutes, 15 after the hour?
Perfect.
Great.
Okay, thank you all. Thanks for the wonderful questions.
Thank you very much.
Okay, great.
Sure. Please go ahead.
Okay, great. This is what we just studied, right? And we argue that there are many mechanisms for that. And I'd like to call this learning to compress, right? This is what neural networks are doing. And they are compressing information that is irrelevant to the task in this case. So you might also call this learning to forget, as you'll see. I use on a slide that we'll see in a second. And so by which I mean learning to compress task irrelevant information, that is, in this case, right, we had many different RAVAs, which were all collapsed together, and many different Erics, which were all collapsed together. The task was to separate RAVAs from Erics. So anything about RAVA in Paris versus RAVA in Switzerland that makes one version of RAVA different from another, well, all that information is collapsed away. The only thing that's left is the category label in these sort of networks. Actually, does anybody have any remarks on that about why what I just said is not completely correct? So again, watch this movie, right? And this is what your brain or the artificial brain is doing, right? These are all the examples of RAVAs and Erics at time step 0. And then we unfold for T time steps, and here's how they're reshaped. Does anybody have a remark on whether this seems to be losing all information that distinguishes one RAVA from the other all the time, or is that information still sort of present in the brain?
It might be present in the weights, but maybe it's compressed by the readout. In this case, it wouldn't be.
Yeah, that's a great point. That's really interesting. Maybe the weights have some special information in them, and they might actually. That's actually a very interesting question, and very nicely pointed out, Tron. And another piece is also, let's think about this as a dynamical process unfolding over time, right? At time step 0 in this recurrent neural network, you have totally all the information about everything, right? If I wanted to know the subtle differences to figure out whether Rava was in Paris or Switzerland, I could do that. That information is there. I might get it wrong because it's a very complicated sort of input, but that information is there at the first time step. And if I would freeze the system after 1 or 2 time steps, then that information is sort of partially there. And it's only at the very end, after 10 time steps or so, that information is completely gone, and I have this categorical representation. And to me, that's actually a massively interesting possibility that was brought up not by me, but by a colleague at a talk like this, is they said, look, you're talking about representations like this, containing lots of information, which is in principle good, but then they're also very high dimensional and perhaps hard to work with and hard to make generalizations from, which is true. You're talking about representations like this as being good because they're very low dimensional and useful in terms of being able to make generalizations to new categories because they'll all get squashed to the same place. What's interesting about a recurrent neural network over time is that it does all of the above, right? If you examine or read out and store its activity at early steps, then it will be the complete representation. And at late steps in time, it'll be the compressed representation. And all that information is available in the same brain area, just at different points in time. So to me, this is mega interesting, right? You might like high dimensional representations, you might like low dimensional representations. Well, this simple theory of network learning in recurrent neural networks suggests that in one brain area in that recurrent system, you have both available just at different points in time. That's cool, right? It wasn't my idea, but I mean, it's sort of obvious from just watching the movie, but I never thought about it that way. Okay, anyway, so you're learning to, yeah, go ahead.
So it's just like, in here also, I mean, it collapses to these 2 points because you set the target was only these 2 labels, right? So like the target of your task was to classify in these 2, but I assume if your target was to say, you just want to classify as a face facing forwards or sideways or the back, then you might have more targets. So it all depends on what you set as a target for the network in the end, no?
Brilliant. And that's a very, very interesting comment because what if you make a really interesting target, right? Like Rava versus Eric, maybe you were kind of interesting, but you're tired of us by now. And anyway, that's sort of 2 obvious categories. Something more interesting might be happy or sad, an emotional content, semantic content, good movie, bad movie. And maybe those are arranged on a spectrum. right? Then in training a network, somehow you are collapsing out all information except that goodness or badness. That's pretty interesting, but still you've defined what the readout should be. We'll get to some examples in a second in the context of prediction, where you're closer to unsupervised learning, but the same type of collapse occurs. And then I think that's really interesting because you're doing a collapse to something that you don't predefine, and therefore maybe learning something about the structure of the data that you, the inputs or the world that you didn't know before. Okay, but anyway, so summary so far, sorry if I'm going slow. I just want to be clear, I only have one message so far, is that these networks learn to compress. Okay, so what is this connected to in terms of the literature? Lots of important work. So here's the work of Schwartz-Ziv and Tishby, the idea of the information bottleneck. And here's a very famous, deservedly so, paper. And the way they discuss compression is in terms of mutual information. And in particular, they argue quite convincingly in this paper, and also via mechanistic analysis that has to do with variability and randomness in very similar ways, that the way what seems to happen when a neural network is learning is not just this former cost function, right? This makes sense, that you'd be maximizing information between hidden layer representations and the task outputs, like the labels. Right, you would believe that learning would converge to that, but automatically, with no regularization, with nothing other than the simple dynamics that I showed you, or the simple updates that I showed you on slide 2 or 3, that it's also like there's this hidden factor which is minimizing the information between the representations and all the details in the task inputs. Okay, so this first term we know, right, that's the learning objective, is to satisfy, is to solve the task. But what Schwartz-Ziv and Tishby argue is that there's this hidden optimization term, or sort of hidden regularizer, which is throwing away all the information, as much information about the inputs as you can, subject to actually solving the task. And if you think about it, that's sort of exactly what we were observing geometrically in these figures. You're throwing away all information about the inputs except for the task, in this case, their category label. The only difference is that Schwartz-Ziv and Tishby are expressing this in terms of information quantities, and we're expressing this in terms of just very directly, maybe in a simpler or more elementary way, in terms of the geometry of where these points lie in their dimension of the set. Okay.
But sorry, just Eric, just a quick question. Are you saying that the two kind of phenomena are similar, or you're saying you can somehow show that the learning rule will actually optimize the bottleneck objective function?
Well, we haven't done anything careful, so this is just a qualitative comment. But I think that this type of dimension compression is one solution to the information bottleneck problem. So I think it is true that if you would study this objective function, which we haven't done, we haven't tried to estimate these entropies, but that this term would be as small as possible, right? This term basically vanishes for these compressing solutions. So I think it's probably true that the type of solutions that we are finding here would optimize this quantity, but we haven't done a careful comparison. Yeah, so I guess what I'm saying is that maybe we have a simple example that we can understand geometrically of why the information bottleneck is happening. But that is not a great achievement, because Schwartz-Ziv and Tishby have real analysis of learning in terms of variability from time step to time step that they show is maximizing this summed quantity. They just do this in a different way. That's directly getting at the entropy. So maybe you could say we have another, maybe simpler way at establishing their results, which they independently developed, and of course are their very good original results. Yeah, Amir, please.
Yeah, thank you very much. There's also a question from Amir.
Yeah, please.
Maybe it's a broad question, but in behavior, we have some sort of selective attention, which reduces the dimension of the input information. how we can think about the selective information with respect to this mutual information optimization.
Yeah, that's really interesting. So is that like, that's like a dynamical thing, which is, it's a dynamic thing, right? Like I'm solving a task, I'm not paying attention, and then suddenly I'm paying attention, then I'm not, then I am, and that changes the dimensionality of the representations. Is that right?
Yeah, more or less.
Yeah. Okay, if you actually, so first of all, that's really cool. I hadn't heard of that. I totally believe it, of course, but if you have any references on that you're able to share, I'd like to study those and understand that better. So thank you for one. Please just send them to me. I'm etsb@uw.edu, or you can just search my name and that's all that comes up. Second of all, how might that actually happen in this case? First of all, I don't know, but so I can only speculate or guess. This is such a great group. This is so fun. Thank you all so much for these questions. So my guess is going to be this, right? So this is your network dynamics, right? It involves a W. The claim, when you're attending to something, you're basically changing the W, right? And why am I changing the W? Am I really like magically growing new connections? Like, of course not, that's crazy. But I'm providing bias input, right, into neurons, probably top-down input. And that is changing the point at which the system is linearized, right? Which neurons are basically taken in and out of the system if you have a nonlinear or saturating function. And so that's really changing the effective connectivity. If I would relinearize the system, it would look like it had a different W. And my guess is that when you are attending to something, your effective network structure is something that is producing lower dimensional activity through its recurrent dynamics than when you're not attending. Now, a question is, why do you actually learn that, right? I mean, what I just said is kind of an obvious comment. Like, it is lower dimensional, so I'm saying that it's made lower dimensional. That didn't really have any content. So how could that actually occur? Maybe what's going on is that attention is also gating learning somehow. And so when it is that you're attending, you're activating this new network, right? Or this new effective network. And that's when the plasticity is happening that does its thing, right? And the thing that it's doing, right, as we've seen through this lecture, might be not just solving the task, but doing compression of input data at the same time. So that's my
thank you.
It's a very nice question. Does that make any sense? Yeah, it's a possibility. Yeah, but I think that's something that many people are thinking about, is like, you know, obviously this goes all the way back to different resting state networks and things like that from the functional imaging literature and other things. The idea that you don't have one brain network, right? That the networks themselves are dynamic. Okay, that's great. Okay, so Schwartz, Ziv, and Tishby. This is supposed to be a school, but even if this was just a normal scientific lecture, must be said to have come first in terms of ideas of compression, and maybe other people too. Okay, now let's see if this also works. I've just shown you things with little Gaussian blobs, right? Blob of Rava, blob of Eric. Do you get the same in a really simple vanilla, one-step recurrent neural network solving this? Does the same phenomenon happen when you have more complicated images, like actual image classification in 10 categories, the CFAR10 database, and a more complicated network? So this is one of these residual networks solving this task. And we think the answer is yes. Here is a paper which is on the archive, another paper which is published, which looks at the same type of question, more work in a similar direction. And then I want to mention a paper I just learned about very recently, which will actually come up on a future slide. But it is from the group of David Donahoe, D-O-N-O-H-O, who's at Stanford. And if you just do this right now, if my lecture is boring or maybe it's really interesting and you want to jump on a reference, you can look up something called Neural Collapse by Donahoe. And that's making, I think, basically exactly the same point. And to the best of my knowledge, that was discovered independently by that group. Okay, and so what is the point? The point is that this still happens, this type of collapse or compression of dimensionality in feed-forward networks doing more complicated tasks. Okay, so remember, we had the back propagation through time before, right? Where one time step was feeding into the next. If you have a multi-layer network, it's basically the same thing, except one layer is feeding into the next. So the same type of ideas apply. It's just that the weights between every time step, now every layer, are different, right? So you can think about a feed-forward network as just like a recurrent network where the weights change at every time step. And then other than that, they're exactly the same thing. So based on that, maybe it shouldn't be surprising for us that if you take a generic initialization of a random neural network, this is from the Seattle group's work, you see an increase in dimensionality, no clear decrease in dimensionality. I ignore this last layer because that's just the readout layer. But once you train a neural network, you see that in the later layers, you see a pronounced decrease in dimensionality, just like we saw in the recurrent neural network simulations. This is actually interesting because first there's an increase in dimensionality, then a decrease. That is probably because these inputs are not linearly separable. So there needs to be some sort of preparation or change in the inputs before they can actually be linearly classified. So you may have two stages of learning. And that's actually something that we study explicitly in this paper that I think I shared with you. We force the inputs to not be linearly separable, and then you get an expansion of dimensionality and then a collapse. So this is a version of the same thing in a much more complicated setting. Okay, how about experiments? And we'll get to some experiments from our group in a second. First, work that's recent from Mansouri and from Friedman and Assad. So they made categories in the following way. So here are categories in terms of images. How about categories in terms of directions? So in this case, non-human primates were trained to do a direction of motion categorization task. And you can either have category 1 or category 2. Category 1 is everything that is to the left of this dotted boundary line, and category 2 is everything to the right of it. And what these authors find is that even though there are dramatic differences between the green lines, which are in the same categories, 120 degrees apart, and there are actually smaller differences, only 60 degrees between one blue and one green direction of motion. The representations of these inputs in the brain of the animal, some intermediate brain area, parietal brain area, do not follow their sort of differences in input space, which would be smaller between this blue and green than between this green and green, but instead are grouped by category, right? So all the greens get mapped together. So this is exactly an example of learning to forget or learning to collapse. If you're in the same category, you get squashed together, even if you're very far apart in the input space. How about some more experimental evidence? This is the work of Merav Stern, who was in Seattle. And she collaborated with many at the Allen Institute on the analysis of data from the following task. It's called a change detection task, which means that when there's a change in the physical environment, then the animal must respond in order to receive a reward. So here's a movie of this. So here we have a mouse, and then you see that the physical environment changed. It went from horizontal background to vertical backgrounds now, and then the animal is receiving a reward. Okay. So the first thing that Merav did was to train a neural network to solve this task, right? And as she did that, she saw that across stages of learning, the dimensionality of network activity decreased in a recurrent neural network similar to those we studied. So similar type of result, but for a different task. And then what she did is analyze the activity in the whole brain. So these are activity patterns as a function of time. This is wide field calcium imaging. So this movie, the intensity that you see at a given location in time at a given point in time is proportional to the average calcium in neurons at that point in time, which itself is roughly proportional to the firing activity of neurons as well as activity and active dendrites, which are providing input to those neurons. So it's sort of a mixed representation of neural activity as a function of space and time. But regardless, it's a vector of neural activity. It's across a good portion of the surface of the activity. And as a vector, you can take its samples at different points in time and ask whether they occupy a high dimensional space or a low dimensional space. And when Rob does this, she sees that across stages of learning, as quantified by the quality of performance on this task, and these are data that are compiled together across multiple days, the activity seems to be decreasing over time as well. The dimension of the activity seems to be decreasing, across stages of learning as well. So the same qualitative effect, but here approximately measured, but measured in a really exciting sense across a large areas of the brain. Marav Stern.
Sorry.
Yeah.
I was wondering, when you say that there's probably changes throughout time, like for the animal, what kind of time scales are we talking about? Like how many trials, hours?
Yeah, these are days. So this is not much data, right? But this is, let's see here, about an hour worth of data, maybe 1 to 2 hours worth of data on day 1. This might be day 2, this might be day 3, this might be day 4, this may be day 5. And as you see, as you go across days, right, so the animal works on this task for a couple hours a day, say, its behavior gradually gets better. And as its behavior gets better, the dimensionality somewhat, right, well, actually by a good amount proportionally, the dimensionality goes down. Okay, I put, to do here, I think in order for these data to really be a convincing test of the hypothesis that this is a signature of learning, as opposed to a signature of simpler behavior or some sort of other factors, significantly more data analysis might need to be done, and some of that may not be possible with existing data. But this, at the very least, is suggestive. And again, Marav, came up with these ideas as well as the ways to test them. Okay, and there's one more thing that I wanted to share, which is very much connects to the questions before about what is happening if the definition of what it is that you're trying to forget is much more complicated. What if we don't really know what the categories are? Again, in the Rava and Eric example, it was sort of easy, right? It's the identity, the label, and then everything else you forget. It's likewise in these category cases. But what if the task is really somehow very poorly defined? What if it's somehow navigating or making predictions in a world which appears complex, but may have some simpler maps or simpler latent structure that's generating it? What do I mean in that case? Well, let's get very concrete. Let's study this task. You are a red dot. Before Rava was a blue dot. Let's say Heloisa, is that your name? Heloisa, okay, so Heloisa gets to be a dot, so congratulations. So Heloisa is this red dot, and she is moving around an environment, and at any moment in time, she looks around, actually she looks straight ahead because she has 2 eyes, and what does she see, right? She sees the edge of her environment. If Heloisa was in her office, which it looks like, or their office, which it looks like they are, then you look around and you see pictures on the wall or the plant behind you or whatever. Here we're just going to abstract that to say, this kind of looks like the water lilies, doesn't it, by Monet. So they have a big Monet picture on their wall, and that's what it looks like. Okay, but the point is, at any moment in time, you're looking at your environment, and you get a very high dimensional observation, which once again is the pixel map in whatever direction you're looking at. Okay. And let's say you're moving around your environment, in this case, randomly, and at any moment in time, you may make a step in some direction and you might rotate as well. Okay. Let's say your task is this. It's not to categorize paintings or detect Rava or anything. It's the following totally unsupervised task. You are trying to predict what's going to happen on the next time step. right? So you're given this view of the orangerie, and when you're visiting Rava, that's what I always do, is go and look at this painting. Actually, I hope he invites me back so I can go look at it again in Paris, in this incredible place. So I'm standing in the orangerie, I'm looking at the water lilies, and I'm going to move my head a little bit, and I would like to predict what is going to be there at the next time step. Actually, that's not a very good example, because who cares what's happening when you're looking at a painting, but if what's happening is I'm moving around the world and I'd like to grab a coffee cup off my desk and not drop it, or I'd like to not slam it into the wall, I need to have a prediction of what that input is going to be at the next time step, so that I can do motor planning one step in advance and other things. Okay, so this idea of training a neural network to predict the future is one that has very natural applications in terms of an objective function that you think an animal might be using in order to survive. It's also a useful objective function because although it's unsupervised, it's something that you can actually train on, right? You can compute the loss of OT plus 1 minus OT plus 1 hat, right? How close am I to solving this task? Simply by remembering what your prediction is and comparing that against the actual prediction, the actual input that will occur one time step into the future. And there's your error signal, which you can use to drive learning. So I think we have reasons to believe that this type of learning objective is plausible. Okay, so it turns out that when you train the animal to solve this task, sorry, let me see if I can get my previous picture up, to solve this task, what is the, you can study the dimensionality of the neural activity and its representations, and it goes down as you learn this task. But what is it going down to, right? For the case of Rava and Eric, it was easy. You say all the Ravas go together, all the Erics go together. If we also had Trong On, then we have 3 different clusters. It'd be a 2-dimensional thing. If we add Gilles in, we have 3 dimensions. Add Gideon, that's 4 or 5 dimensions, whatever, right? But here, what are the categories? There aren't categories, but the dimension is going down. What is the dimension going down to? And I believe I shared this paper, but this is the work of Mattia Ragati and Stefano Raccanatesi, and it's in Nature Communications in 2020, and I'm a little part of the story too. And the title is Predictive Learning Extracts Low-Dimensional Latent Space Representations. And so what this paper finds is that this neural activity collapses to a low-dimensional set, but that set has a dimensionality which is related to the number of latent variables that are generating the data. So what am I talking about? So here we go back to Heloisa in their office, and the red dot is moving around, right? From one place to the next, looking around. And as that happens, how many different things are changing in order to generate this picture of the wall? Answer, X and Y, the position in physical space, plus theta, an additional rotational variable, right? So there's a 3-dimensional, even though these observations are super high dimensional, right? They are as many pixels as you have, again, 1 million if Heloisa has megapixel eyes. These are actually being generated by a low dimensional process that's evolving in 3 dimensions, X, Y, and theta. And it turns out that the dimensionality of this activity collapses not down to exactly 3 dimensions, but pretty close, maybe to 4 or something like that. And moreover, these hidden unit representations can be mapped onto the physical space in the arena where the image is being generated from. In a sense, it sort of feels like grid cells or something like that are emerging, but they're not grid cells. They are something different. It's a and the process of this emergence, we believe, is closely connected to the idea of collapse. The idea that the different images that are mapped together to the next time step, in a sense, that belong to the same category, are those images that come from nearby points in the physical space. So I think there's a relationship between what we talked about in terms of categories getting collapsed together and the emergence of these low dimensional latent space representations. The effect of categories when you're navigating a latent space are the categories of points that are grouped together are the categories of points that are nearby one another, because it's only the nearby points at time t that could eventually give rise to the same observation at the next time step, t+1. So the categories of points when you're making predictions are the sets of inputs that could produce the same thing on the next time step because they belong to the same category. And inputs that then belong to the same category, if you have a smoothly varying environment, will tend to be those that are generated from a similar place in whatever latent structure is generating the data. So to me, this is the most interesting possible future direction of research in this area, and one of the most interesting ones that anybody has ever told me about, right? This is the work of other people, largely that brought it to our group, and then we worked on it together. The idea is that categories in dynamic data can be automatically formed. Categories, again, being all of those different inputs that would lead to similar outputs on the next time step. And if you're doing that prediction, it's sort of like doing a categorization of inputs on one time step to the next. If you're doing that prediction in a recurrent neural network, you won't just solve that prediction. You will compress out all the detail, all the information that is not necessary in order to make that categorization. So you'll throw together all the details of the water lilies and just preserve information about where in physical space this image of the water lilies is actually generated. And to me, that's really, really interesting, because that suggests that you can walk into a totally new environment, maybe an abstract environment, maybe an environment that has more than just physical location. Maybe it's the environment of the restaurants of Paris. I'm not kidding. And the inputs are gustatory inputs. They're the tastes and the smells. And there are certain ones that are related to one another and certain ones that are not. But we have absolutely no idea what the dimensionality of that space is, the latent space that's generating all these delicious tastes and these delicious smells. It is possible that if you have a neural network that is doing the simplest thing, which is just learning to make predictions, then as a consequence of making predictions, the internal representations in that network will have formed the simplest possible representation and really an actual physical or geometrical map of all of those input data. So you can build what is called a cognitive map, perhaps just by virtue of making these predictions. Okay, that is the idea of this work. Okay, it is time for me to summarize, and I do so on everything I said on this task. On this slide. All right, so part two, so what are we doing? We are studying network dynamics, period, right? Because we think that the brain, or at least brain-like structures of interest, are networks. So we are not doing abstract sort of machine learning or mathematical statistics. We are very, very concrete, and we are saying we are looking at representations or activity patterns that are formed in networks. Okay, and the second part of this lecture was a top-down lecture, a top-down perspective, where we say that whatever the networks are structured, however the networks are structured, they are structured in that way because they have learned to perform a particular task, right? And then we ask again, what is the number of degrees of freedom in the network activity that follows from learning that task? Okay, we studied for most of the day before coffee what we called an easy classification task, right? And that is a task in which there is no reason to change the representation. None. You could just read it out on the sample data that you're being trained on and get 100% accuracy. But you don't do that. You massively change the representation. You squash it so that inputs that belong to the same category are grouped together. Massive collapse of dimensionality. This occurs in what we call task irrelevant directions, which are directions that are orthogonal to R, so that all you have left is the task relevant information. Everything else has been compressed away. We think this may be useful in terms of creating highly compact representations that enable generalization. We notice how that is perhaps just a specific example of an idea in a mathematical analysis that had already been proposed. We saw through the work of Merav Stern and also through some work from the Chicago group of David Friedman that this may be a signature of the way real brains are actually learning as well. It's different, actually, I wish Mitra was still here, but it is distinct from other types of learning rules. And that doesn't mean that there's a fight in which these people are wrong and then the compression people are right, or we're wrong and they're right. And no, certainly throughout the brain and throughout brain areas and different tasks and different environmental conditions, you're going to have different types of learning rules. And it may not always be the case that you get this compression. And these seem to be cases where that does not occur. And that's good. Another interesting paper by Cueva I recommend studying, and Stefano Fuzzi. Actually, it's an extremely interesting recent work. Very interesting. As a matter of fact, I think there's a preprint by Fuzzi called The Geometry of Abstraction from the Columbia group. How can you have a more interesting title than that? And that's very similar to these results. And it's a little bit shocking that I didn't give a full citation to that. Sorry about that. Fuzzi site ad. Okay. We observed this mostly for recurrent neural networks, but we saw that the same type of trend is there in deep networks. And we realized that there are other people who have also made this observation. I mentioned a paper by Donahoe's group. That's this one. So there you'll see neural collapse in PNAS from last year. And we saw that the same trend also occurs for predictive learning. And so that I think is really, really interesting because again, in that case, the categories are not defined in advance. And there are really effective categories that seem, our hypothesis is that these effective categories are the categories that are pulled together. The samples that are pulled together, the inputs that are pulled together belong to the same effective category. And the meaning of effective category is you might get mapped to the same output at the next time step. And that is super important because that's an automatic organization of inputs that are close by in time, and a compression of anything about those inputs that does not make them close by in time. Sort of sounds like manifold learning or isomap or whatever. But these are objective functions that you put directly into a statistical learning package. Here we're saying just take a recurrent neural network and ask it to make predictions, and this type of collapse will happen automatically within the network due to the dynamical properties that we talked about today. Okay, what did we do on Monday or so? We studied connectivity from this dimensionality question and compression question from a bottom-up point of view. Right? And we saw that there are many important contributors who point out low rank structure, spatiotemporal dynamics as important factors that lead to dimensionality. We propose that network motifs are a general theory. Nobody has really gone into those other cases which have been published in the literature and asked whether motifs are good enough to explain those results in a huge amount of detail. Although there's been some work like that that's been done. So this is a proposal of a general approach, and it's been tested a little bit, but should be and could be tested more. I want to leave with a following idea of a possible connection between Monday's talk and today's talk, but really what we really mean by this is a possible connection between a top-down and a bottom-up perspective. So we argued that these sort of intermediate dimensions in which you've thrown away a lot of information, but not all the information, and you've kept information that's relevant to a task. These Goldilocks dimensions may emerge via mechanisms which are local in their nature. So what do we mean? So in this first part of the talk, we said that dimensionality can be predicted by measuring a bunch of different local structures, these converging chain and other motifs, and putting them together into some formula. But the basic idea is that these local structures that add up to control the dimensionality across the network. Now, how does plasticity actually work in biology? Well, it works in all kinds of fantastic ways, but the ways that have been most studied are local, right? The relationships between spike times in directly connected sets of neurons. And that is very different from the type of learning rules that occur in a top-down perspective, where you just take the gradient of the entire network activity and you do whatever update the gradient tells you should, with omniscient information about what all the neurons are doing everywhere in the network at all points in time, and you use that update, right? That is probably not the way that learning actually works in the real brain, and it's probably some sort of approximation of that by necessity is more local, because again, all that activity and connectivity information is not magically transported over the brain. I'm obviously not the first person to say this. This is what everybody in the community is saying now. So what's interesting to me is that dimensionality is just a number, right? It's not the only thing that matters, but it probably is really an important factor in terms of forming representations, again, that don't just solve the tasks, but are useful. For example, contain the cognitive map, contain the X, Y, theta coordinates in Heloise's office, as opposed to all the super complicated information about what type of plant she has on the wall, which is not relevant necessarily to my navigation problem. So this connection makes it possible that plasticity mechanisms, which are more biological and therefore which are local, can contribute to the control of this property, this dimensionality across the whole network. And whether or not that is actually used in terms of actually learning tasks is an open question and one for the future. And the first thing to do would be to actually ask in these cases whether motifs are changing in some systematic way. And then a deeper thing to do would be to actually argue that there are local rules that can take advantage of the local control over global dimensionality in order to do this type of learning. That's a pipe dream. Probably nothing like that paper will ever be written, but I wanted to indicate this connection between the two because we all have mathematical and theoretical backgrounds. We'd like to think about things in both bottom-up and top-down ways. We will make progress, I think, as a field when we figure out better ways to make those connections. And this is just sort of an imaginary example, perhaps, of how those connections might be made. Okay, I'll leave with this. I just want to say that this is, I get to stand here. First of all, this is the work of the community. So I did my best to try to combine references from the community as well as concentrating on work that was done with some connection to Seattle, so I can give a personal perspective on it. But let's just read some names. So Stefano Recanatesi was involved with much of this work. He is an amazing scholar at the University of Washington. Likewise, Matt Farrell. Marav Stern independently developed many important ideas about dimensionality in a very inspiring and impactful way, and also tested those ideas. Michael Bice and Gabe Ocker have worked on extensions of the motif theory to nonlinear networks. Yu Hu, who is a former director of the summer school, is now in Hong Kong, and entirely his work then just sort of explained to me in my office and taught to me led to all of the results about motifs. Madhu Advani, who was then at Harvard, developed mathematical connections between variability and compression together with Matt and Stefano. Guillaume Lejoie contributed important insights about nonlinear network dynamics, as well as machine learning to these studies. Raba's colleague, Sophie Deneve, is instrumental in terms of thinking about latent variable models of the world and how they're dynamically learned, and is an author on the predictive learning work. And Mattia Rigatti and Stefano deserve the credit for originating the project on dimensionality and latent variables, which I think is the most interesting and important part of the talk. And once again, is not one that, although I wish that I came up with. It is these workers and thinkers who deserve all the credit. I'm just a mouthpiece, And an important thing to say is that some of this work was supported by a private individual who will be missed. And the other work was supported by the citizens and taxpayers of our small world. So thanks to everybody who's making this possible, and especially you for listening. And we have 90 seconds for further discussion. How's that for staying on time, Rava?
Thank you so much, Eric. Thank you really very, very much. It was wonderful. You must be quite tired after such a sequence of lectures. If you have 1 minute, maybe if there are 1 or 2 pressing questions.
I saw that Eloisa and Amir had their hands up.
I think they were clapping.
Yeah, I was applauding. Yeah.
Okay, well, I've got to say, I'm very satisfied. These I actually wrote down just a couple things, but I'm going to immediately type in some other things. These are really good questions. So you all are clearly understanding this. And through the opportunity to present this work, as usual, you have a chance yourself to challenge your understanding and see what you need to do and what you don't really understand. And so it's a great gift to me to get to share this with you. It actually helps our research a lot. So thanks a lot for listening. I'm grateful for that and for the questions. And whenever we can ever go anywhere, all of you, would be wonderful if you're coming through Seattle. Look us up, and it would be wonderful to interact. But otherwise, we'll just do this virtually. If anybody wants to follow up or ask any questions or email or whatever, or Zoom, it'd be my pleasure. So thanks a lot. Thanks for the opportunity to the audience.
Thank you again, Eric. I think everybody got a huge amount from all your lectures, also from the discussion. So thank you very, very much. And as you suggested, I should invite you again to Europe. So I have a number of questions. I won't tire you now with them, but you visit and then we'll talk. That would be very nice.
Only if there's delicious gustatory world mapping research.
Sure, with pleasure.
Done. Bye-bye.
Thank you again. Thank you. Bye-bye. See you all tomorrow. Bye-bye. Thank you, Eric.